In this video, I'm going to be talking about evaluating limits analytically. By analytically, I mean we're going to be evaluating these limits without looking at the graph of the function. To start off, I am starting with a piecewise function example, and I am showing the picture just to show you the connection between the graph and what we're going to be doing analytically. So, in previous videos, I've discussed that the value of the function is not necessarily the limit at that x value. We see here we have this special case where x equals 0 here. Since we're approaching a different value from the left and from the right here, we know that the limit does not exist. But here we see that the value of our function, so the value of my function at 0, we see is equal to 1. So we see there's a difference between the value of the function there and the limit at 0. However, at every other place on this graph, it's true that the value of the function is equal to the limit at that point. For instance, here, if I look at the value of my function at x equals 1, I see that it's equal to 2. And if I were to talk about the limit as x approaches 1 of my function f of x, well, I see that from the left and from the right, I'm approaching 2, so that is my limit. What's special about the graph where the value of the function is equal to the limit is that it's continuous, meaning that I can trace along my curve at all those points without picking up my pencil. We see where I had to pick up my pencil, the limit was not equal to the value of the function there, but everywhere else, the limit's going to be equal to the value of the function. So analytically, without graphing my function, if you're given a limit, the first thing that you're going to do is just plug it in. So what I mean by that is if we're given the limit as x approaches 1 of x squared plus 4, the first thing I'm going to do is I'm just going to plug in that x value. So I plug in 1 squared plus 4, this equals 5. If I get a finite value, that is my limit. So the limit as x approaches 1 of x squared plus 4 is equal to 5. Let's look at just a couple more examples just to get the point across. For instance, if I have the limit as x approaches 1 of x squared plus 2 divided by 3x minus 1, just going to plug in 1 here for x. I get 1 squared plus 2 divided by 3 times 1 minus 1. This gives me 3 divided by 2. I found a finite value. Again, that's my limit. Same thing goes for different types of functions. Say I'm looking at the limit as x approaches pi over 3 of sine of x. I just plug it in. I have to remember my trig values, my unit circle. The sine of pi over 3, if you recall, is the square root of 3 over 2, and that is the limit here as well. So the first thing that you're always going to do whenever you're given a limit problem is just plug in that x value into the function. Now, most of the time, you're going to be looking at special cases where you don't just end up with a finite value, but that's always your starting point. So let's look at a couple of examples where we have a special case. Our first example is the limit as x approaches 2 of x squared plus x minus 6 divided by x minus 2. So first thing we always do is we plug in that x value of 2 for x, and we will have 2 squared plus 2 minus 6 divided by 2 minus 2. And here, 2 squared is 4 plus 2 gives me 6, minus 6 gives me 0, and then 2 minus 2 is 0. So I have the form 0 divided by 0, which tells me there might be something else going on as x approaches 2 of my function. I have to do something else to determine the limit. And we call this the indeterminate form. Okay, so maybe there's a hole in my function there. We don't know. We have to do something else to the function in order to determine what the limit is. I'm not going to talk about what we do in this example, but I just want to show one of those special cases. Another special case is, let's look at this next example. If I have the limit as x approaches 1 of x plus 6 divided by x squared minus 2x plus 1. Okay, so here, first thing I always do, I plug in my x value. I have 1 plus 6 divided by 1 squared minus 2 times 1 plus 1. And my numerator, I have 1 plus 6 gives me 7. And the denominator, I have 1 minus 2 gives me negative 1 plus 1 gives me 0. Okay, so here we have 0 in the denominator, which we never want to be dividing by 0 in math class. It tells us that, again, something else is going on, and I'm going to have another video about this. This actually means that you have an infinite limit. So be looking out for future videos that are titled Infinite Limits, and also I'll be showing some different examples of how to solve limit problems analytically when they are in indeterminate form.